Okay, problem number 48 in your textbook. So you'll find this on page 315. It's the end of chapter 10 assessment. So problem number 48. Let's take a look. So the problem's asking us to name the representative particle of each substance. And representative particles are, depending on what kind of substance, it could be an atom, a molecule, a formula unit, or even an ion. Okay, so this is number 48. A. Oxygen gas. So oxygen gas, as we know, is the formula O2. It's a diatomic, and so this is a molecular compound. Okay, so the answer would be, so the representative particle would be molecule. Okay, B. Sodium sulfide. Sodium sulfide. So that is not a molecular compound. Sodium is a metal, so that is an ionic compound, and so the representative particle would be a formula unit. So formula unit. And the abbreviation for formula unit is F period U period. Okay. C. Sulfur dioxide. Sulfur dioxide. Okay, so neither one of these elements is a metal, so with two nonmetals that makes a molecular substance, and so again the representative particle is molecule. And D. Potassium. This would be, that's just a pure metal, potassium, and so here the representative particle would be the atom. Okay, so hopefully you did okay on those. The next problem is number 50. 50. All right, and the question is asking which contains more molecules: 1 mole of H2O2, 1 mole of C2H6, or 1 mole of CO. Okay, so first of all, just so you know, H2O2, that's hydrogen peroxide, and hydrogen peroxide is a molecular compound. C2H6, that's the molecule ethane. That's the hydrocarbon with 2 carbons attached. And that is definitely a molecular compound. And then, as you know, CO is carbon monoxide, which is molecular. And in all 3 cases, we're saying how many molecules, or which one contains more molecules if you have 1.00 moles of each. Well, it's not meant to be a trick question. It's but the answer is it's really pretty simple if you really understand the concept of the mole and a molecule. So let's take these one at a time. So if you have 1.00 moles of hydrogen peroxide, then you have 6.02 times 10 to the 23rd hydrogen peroxide molecules. Moving down to ethane, if you have 1.0 moles of methane molecules, you have 6.02 times 10 to the 23rd molecules of ethane. And likewise, if you have 1.00 moles of carbon monoxide, you have 6.02 times 10 to the 23rd molecules of carbon monoxide. So you actually have the same number. If you have 1 mole of each of these compounds, then you have Avogadro's number of each one of those, and therefore you have the same number of molecules in each one. So none of these samples contains more molecules than the other. They all contain exactly equal numbers of molecules. Okay, so that's number 50. All right, let's move on to number 51, I guess. Okay, 51. Okay, so now the question is actually, there's a subtle difference. It seems like we're talking about Well, we are talking about the same three substances as we did in question number 50. But this time, the question is asking not about molecules, but it's asking which sample would contain more atoms. Okay, so let's write those down again. So we have hydrogen peroxide, ethane, and carbon monoxide. Okay, and the question is asking us about the number of atoms, not molecules. Okay, so first of all, let's just take this on a molecule by molecule basis. If we had one molecule of each one of these three substances, which molecule has the most atoms? Okay, so if we do this systematically, hydrogen peroxide has 2 hydrogens, 2 oxygens for a total of 4 atoms. Ethane has 2 carbons, 6 hydrogens, that's 8 atoms in total. Carbon monoxide, 1 of carbon, 1 of oxygen, so that's 2 atoms. Okay, so clearly, if we're just talking about single molecules, ethane's the winner. It has 8 atoms. Now, let's take this step by step. If I said, hey, I have 1 dozen of each of these substances, 1 dozen molecules of each of these 3 substances, which collection would contain the most atoms? Well, clearly, if you had 1 dozen molecules of hydrogen peroxide, you'd have 12 times 4, or 48 atoms, right? If you had 1 dozen molecules of ethane, you'd have 12 times 8, or 96 atoms of ethane, and you'd have 24 atoms of carbon monoxide. So then, if we just extend this let me erase this. If you extend this one more step, and you say, well, now, what if you had 1 mole of each substance? You'd have 4 times Avogadro's number of atoms in hydrogen peroxide. You would have 8 times Avogadro's number of atoms in ethane, 2 times Avogadro's number of atoms in carbon monoxide. So here, the winner is ethane. Ethane, whether you're talking about a single molecule, dozens of molecules, or a mole of molecules, among these 3, ethane packs the most atoms per molecule. Okay? All right, let's go to the next slide here. Now, the next problem is number 53, and we're being asked to calculate the molar mass of each substance. Okay, so 53A. 53A. H3PO4. This is phosphoric acid. Okay, and this one I'll do this one step by step, and then I'll probably just give you the answers for the rest. This one, let's take each atom or each element one at a time. Okay, so we have 3 hydrogen atoms, and each hydrogen atom has an atomic mass of 1.0 if we round it to the first decimal place. So that's the hydrogens are contributing a mass of 3. Phosphorus, there's only 1 phosphorus atom in here, and phosphorus, if we look it up in the periodic table and round to the nearest tenth, has an atomic mass of 31.0. We only have 1, so its total contribution is 31.0. Oxygen, we have 4 oxygens, okay, and each oxygen is contributing 16.0, which is a total of 64. And when we add everything up, we get 98.0 grams. Okay. Now, one thing I want to make clear on this first one is what this means is if we have 1 mole or Avogadro's number of H3PO4 molecules, that would have a mass of 98.0 grams. So this is an equivalence statement that is very important, and as you've seen, we would use this a lot when we're converting between mass and moles to mass. The other thing I want to mention is a convention, a format for units when we're indicating molar mass. So if we go back to the question and we read, it says calculate the molar mass of each substance. So the molar mass, and this is something that we haven't mentioned explicitly in class, but I want to mention it here. Formally, the unit is grams per mole. Okay, so if you're talking about phosphoric acid, the molar mass is 98.0 grams per mole, and I think you can see, why it's grams per mole, right? So if you have 1 mole, the equivalent mass is 98.0 grams. For every mole, you're going to get 98 grams. Okay. All right. Now let's go to part B. Part B is asking about dinitrogen trioxide and the dinitrogen trioxide, and the molar mass is 76.0 grams per mole. C. This is calcium carbonate, and the molar mass of calcium carbonate is 100.1 grams per mole. Okay, so, and don't forget, if we look up how did we get that? 3 oxygens at 16.0 each, so that's 48 grams from the oxygens. Carbon adds 12.0. Calcium, if you round it to the nearest 10th place, that would be 40.1. And when you add those 3 quantities together, you get 100.1 grams per mole. Okay, we're moving along great. Okay, the next one is ammonium sulfate. That's D. Let me get my pen back. D. Ammonium. Oops, sorry. Let me do that over. So ammonium, that's a polyatomic ion. NH4, we have 2 of them to balance the 2- charge on sulfate. Okay, and this one, so here, just talking through it, you have 2 nitrogens. You have 2 times 4 or 8 hydrogens. 1 sulfur, 4 oxygens. And when you add everything up, the molar mass is 132.1, and that's grams per mole. Okay. E. This one, let's see, C4H9O2. All right, so here, that's pretty straightforward. When you add everything up, you should get 89.0 grams per mole. F. Molecular bromine. So that's the diatomic form. Bromine, 79.9 grams per mole. That's for 1 atom. And since you have 2 atoms, then that would be twice that, which is 159.8 grams per mole. Okay, so hopefully we did okay on number 53. So this is like, these are very, sort of fundamental, basic operations that, you got to be able to calculate a molar mass easily and, relatively quickly. Now, when we go to 58 in the next video, 58 and 59, we'll use those molar masses to do mass to moles, moles to mass conversions. Okay, see you there.